And
And what did they use?
sorry,
What did they use?
now they're using the advanced, they use neural networks, but not the traditional ones. Like if you see my lecture, most of it was on traditional ones.
Yeah.
Because this is the, obviously you or any other MSc students or PhD students, if they are not from IT, they have to start from the basics. Okay, but like in terms of application, so you have the advanced forms of neural networks, convolutional, uh, deep learning, and all of them are deep learning. But now we have the like grid-based neural network, the convolutional neural network. I mentioned some of them in my talk, but very briefly because I told there as well. I'm not an IT guy, not a computer engineer or something. So I know like the basic difference and so on. If you ask me, okay, explain from start, I will not. Even if I try to do it, I will need like more time. But for your case, for the sake of applying it, it looks very convenient to apply the simple neural networks, but people have progressed a lot more now, and they can see the results. The simple neural networks, like I mentioned, there are even I showed in my results as well. They do not work every time. Sometimes their accuracy can be not even better than the simple equations. Okay, I found in my research as well, and sometimes they are like almost same. Again, no advantage. Why would I go from a simple equation to doing blah 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 with programming? But the new deep neural networks are they are, and they are of different types. The deep ones are also different types. The most easiest one is you take a simple one. I mentioned you add more layers, it becomes a deep neural network. That's the simplest one. Okay, but now people are using many others. Okay.
It's still the same process. And but
Sorry.
it's still the same process.
Yeah.
It isn't.
Yeah, they obviously that's why they are called the neural networks. The process is same, but how it is handled, that has changed. How the process, how the layers are handled, how the process is handled, is changed. Okay, so for example, grid based. So you have the whole grid of layers. It's not one. It's not one layer after another and so on. It's whole grid. So change and yeah, I know. Okay, this is a neural network. Neural network means signals will come from here, processing, coefficient bias, output. This is a process, obviously. But when you have a more complicated architecture, more complicated structures, then you have more variables. Okay. So sometimes I look at the parameters of the model, it goes over my head. Yeah, simple, I understand. Okay, learning rate, number of trials, number of neurons, I understand. But then there is something more, which is because of this type. Oh, I don't. But anyways, you can still use it. I'm talking about your research now. You decide to use some of these techniques for your research, then try to go beyond the simple neural networks. Okay. So now we move on to the next topic, which is correlation and regression. Okay, and these are the sources. So the examples are taken from research papers. Okay, so why do we use ANOVA? We discussed ANOVA and t-tests and the experimental design last time. So why do we use ANOVA?
Yeah.
Multiple groups, yes, comparative groups, and it is based on values. Okay, what type of variables the ANOVA requires? Okay. No, mean is a statistic. What type of variables?
It's not
Yeah.
experimental, which is presented.
Sorry,
Giving the data.
the type of variables.
Experimental, which is the dependence.
We give it some other name. What you're saying is correct. There was another name to get into it. We have the population, we have the sample, we have the extraneous variables which we do not change. Okay, and then we have the observed ones, and then we have the treatment. Okay, so these are the different variables. So when you have a NOVA in front of you, there was an homework and there was an example as well. Like you have to write it. Okay, how did you do it? What did we test and so on? So that is important for research. Okay, so when you look at ANOVA, these are things which should come into your mind. When you are thinking about applying ANOVA, these are things which should come in your mind. Okay, this is part of experimental design. Okay, that you can separate the variables that you need and then you can do it. Okay, so an example as related to the use of AI. So I mentioned it for my other research as well. I saw it for somebody else's work few days ago. So she developed a model using it's a tree-based model, and then her test accuracy was very low. You know, test and training is right? Her test accuracy was low, not very low, low. Okay, training was very good. Like R square was 0.99. For the test, it was 0.7 something. So 0.9, 0.7. So there are differences. She said, I want to make it better. Okay. So she asked our dear AI, what should I do? I said, okay, you can do feature engineering, you can do ensemble, you can do this. Okay. Yeah. And then in the end, because it's very efficient, it wants to ruin your life at no cost. So I said, okay, this is a program which will do everything. What you asked. Okay. She took it, she ran it. Okay. And she got good results. But one of the things the program did, she was predicting cost. So her output was cost. Her input was area. If the area is this much, the cost should be this much with other variables. The area, the number of flows, number of so, okay. When the AI suggested I will do feature engineering, another thing which you need to keep in mind, if the AI says do feature engineering, say no. It doesn't know what you're talking about. Okay. Whatever feature means whatever playing you have to do the variables, do it yourself. Okay. Don't let the program do it. It has happened to me and it has happened to her as well. So my point was the cost was output. This has to be predicted, right? So when I give the input, this is unknown, right? This is unknown. When it did feature engineering, what did it do? It took cost and area. It calculated per unit area cost. Per unit area cost. This is fine. This is total cost. Okay, I will not predict total cost. I'll predict per unit area cost. Per meter, whatever. Square meter. But then it did something very drastic. It said it is still predicting total cost. And the input is per unit area cost. Like if I give you per unit area, you can give me total cost. I don't need any model for that. And the accuracy was 0.9. Okay. So the point was the thing which because of which I mentioned, you must know your variables yourself. Okay. And then you have to divide them like we did. This is my sample, this is my population, this is extraneous variable, this is this is this. So, this is totally up to you. Okay, you have to control these things. Even if you are using the AI technique and even if you are using ChatGPT or whatever to give you the solutions, they cannot work with these things. Okay, so that's why the definition of the variables is very, very important. And you have to handle it from start to end completely. As an example, again, from her work was she was She was taking what? Yeah, she was putting input percentage of cost from the form work. Okay, so normally when there's a construction project, you are working, right? Both of you are working. What is the percentage of form work in the cost of the total project? Huh? How much? Not a lot is what? 50%, not a lot. 10? Yeah, okay. So she took a number like this. Okay, and she put it as an input. Okay, so the form work cost is what? 10% of total. And I'm predicting total. So if I give you the 10% and ask you for the total, there's no problem, right? Okay, so she was putting a variable which was already dependent upon the output. Okay, so the point being, you have to keep these things in your mind and you have to handle them yourself. Okay. Yeah. So there is a need. So the ANOVA or t-test or whatever we have seen up till now, they give us whether there's a difference or no difference, whether there's effect or no effect. Okay. But we still need to know more about it. Okay. The type of effect. We still need to see what type of effect we have. Okay. Right now, we are just discussing continuous variables. Okay. Do you remember the types of variables according to the continuous and what else? Discrete.
So,
No.
the ratio.
Ratio. Ordinal. Nominal. Okay. So right now we are just discussing continuous variable, which is the ratio. Okay. So obviously there are other techniques to analyze the impact of discrete variables, ordinal, nominal. We have other techniques for that. But regression and correlation is mainly between continuous variables. Okay. Now, let's say I have 3 types of administrators. Okay, I'm going to do ANOVA, regression, correlation, something. I'll put them in Excel, right? Or whatever. I'll say, okay, this is mix number 1, or admission number 1, admission number 2, admission number 3. And in my data, I put it as 1, 2, and 3. 1, 2, and these are numbers. Okay. Does it mean because I replaced the admixture name with numbers, does it become a continuous variable? Why not? Because they are different. Okay. Because whenever we put numbers, okay, and we treat them as a variable, then that means the order will follow.
Yeah.
Okay. So 2 is higher than 1. But admixture 2 is not higher than admixture 1. Okay, so there is no relation. So the most common mistake in this case is people put numbers for identification. These are numbers as codes, not numbers as values.
What letters? A, B, C.
Whatever. Okay. Because you put letters and then you put in the software says, I cannot do correlation. But this is the first thing, the most easiest thing you can do. Okay, I will change numbers. I'll change the letters with numbers. So it will do correlation, obviously. It will do correlation, it will do regression. But again, going back to the same point, what you did is wrong. And you should know it. You should know. Yeah, you should know the type. Okay. So this is for continuous variables, which are actually continuous variables, which have values in them. Okay. So we have the ANOVA or the t-test predicts a continuous dependent variable from a categorical independent variable. So there are 2 sets, right? 2 sets or 3 sets. Okay, so these sets are different by what? They are different by the type of treatment, right? We call it treatment. Okay, so the treatment itself is the categorical variable. Yes or no, right?
Yes.
Treatment A or treatment B or treatment C. Okay, the type of steel or the type of admixture. Okay, so these tests are used to find out the effect of categorical variable on the continuous output. Okay, keep in mind the effect is categorical, but the output is continuous, numerically. Okay, now so this should maintain. Okay, you cannot or you should not use t-test and ANOVA to get the output of continuous upon continuous. It's not for that, and should not use it for getting the effect of continuous upon categorical. You cannot reverse it. Okay, in both cases it will not work. Okay, so but we can use in those cases we can use regression. Okay, we can use regression. Now regression means what? It's a line. Regression.
The relationship
The
between
lines. Or the word regression means what?
the relationship between all the points over there.
No,
That's like approximate
like in English.
regression.
Yeah.
Like going backwards or
Yes. Going back and forth.
Yeah.
Okay. Regret. Okay. Good. I never thought about it like this. I know the meaning. But I didn't thought about it. It's coming from regret. Anyways. So yeah, going back and forth. Regression means going back and forth. So keep this in mind when you look at the equation and fitting of the line and so forth. So regression, you are predicting continuous discrete value, dependent variable from one or more continuous independent variables. Okay, the main job is this. The main job is this. If you change it, okay, so you can change the technique. It's much more recommended that if your output is not continuous or one of the inputs is not continuous, okay, it's better to not use it. Better to not, but if you use it, then at least the output should not be categorical. The output should not be categorical. We have other methods for that. I can show you later on. Okay, that is also called regression, by the way. There's a regression for continuous output and there's a regression for categorical output, but they are different and the function is also different. Okay. So the goal is to model and quantify the relationship between variables so we can predict the value on the basis of inputs and we can understand what is happening. Okay, so if you have water cement ratio and you have let's say strength of the concrete is the output. Okay, so you have the water cement ratio, you have the aggregate size, okay, you have the cement type, okay, and the weight of the cement and so on. So these are the input variables. Okay, so if I increase water cement ratio, what will happen to the strength? Okay, so the regression equation can give you this. Okay, and which one has more effect? So you have the
weights.
Aggregate size, yes, weights, coefficients. Okay, I have the aggregate size and I have the water cement ratio. Both of them have a positive effect. Let's see, have a positive effect. But this one has more positive effect. This one has less. This is the idea behind it. But well, now it has happened to be a lot. Okay. For example, one of the variables is income. The other variable is age. One is income, other one is age. Income should be, mashallah, tabarakallah, in thousands, hundreds. Agreed?
Yeah.
I don't know, maybe you are already getting thousands. Okay, but whatever. Okay, it's and the age will be even with all the mashallah, tabarakallah.
Yeah.
It will be like less than 100, right? More than 100 and then you are in the other category, right? You are,
Then
huh? Yes, Jannah, inshallah. Yes. Okay, but if somebody is Jannah, I will not be talking about his age and income, right? I'm saying that, okay, if he crossed 100 and he's still alive, then he is like he has done the full cycle now, right? Okay, say after you become so old, you go back to the childhood, right? So there is no income and there is no age now. Anyways, but the point is you can see the scales are very different. Both of them are continuous. Both of them are continuous. There's no problem in putting them in the equation. Okay. But now, if you look at the coefficients, the coefficient of which one, if they have the same effect, the age and the income have the same effect. Both of them have positive effect, let's say, on the output. Okay. And let's say the amount of effect is also the same. But one of the two variables will have more weight in the equation. Which one? I'm talking about income and age. You say water cement. Very good.
Income and age. And what's the output?
Whatever the output is, whatever. Water cement is output. No problem. Whatever the output is. Okay, just imagine. Okay, whatever the output is, no problem. Which one will, if let's say income and age have the same effect on the output, whatever the output is, they have the same effect. Okay, in terms of magnitude and in terms of sign. If this one is positive, this one is also positive. Okay, this one and whatever the effect is, they have same. But when you will run it in the equation, when you run the model and you prepare the model, one of them will by default have a higher coefficient. The effect is same, coefficient is higher.
The one. So if income is depending on age, this is.
No, there's no such thing like this. If obviously, yeah, it's a good point. If they have relation between them, then you should not put both of them in the equation. We will talk about later. But let's say both of them are completely separate. Okay, or if you cannot digest this example, go back to the water cement ratio. You have the strength, output is strength. Now everything will be clear, right? Because we are talking about concrete,
Yeah.
not people. People will go to Jannah. They will not need concrete. So you have the strength of concrete, you have the water cement ratio. Water cement ratio will be point something.
0.4.
Okay. And you have the weight of aggregators or unit weight of aggregate, which will be something 1,000 kilogram per cubic meter. You see the difference in scale. Okay. I'm saying if both these variables have the same effect on concrete, okay, there's a very high chance that one of them will always have a higher coefficient than the other, even if the effect are same. Which one? Water cement ratio, and you have the unit weight of aggregate. One is in decimals, the other one is in thousands. Which one will have higher variable, higher coefficient by default? The one in decimals. Because the one which is which is already in thousand, it doesn't need a big coefficient to make the effect. Yeah. Okay, but there can be many examples like this. Okay, there can be many. I already gave the example of the unacceptable example, the uncomprehendable example of age and income, right? Which you guys don't like.
Yeah.
But the point being, there can be many cases in which you have to look at the scale of the scale of the values
in comparison
to the other when you are reading the coefficients.
To the other or to the output? To the other.
Sorry.
To the other or to the output as well?
The coefficient is the effect on the output, right?
Yeah.
Okay. But that can be misleading if there is too much difference in the scale of the variables. Okay. So if I'm comparing unit weights of aggregate and cement and water,
So for
they are in the same scale. Okay. So the coefficients will make more sense.
For age and income, age will have
More. Okay. Because the model will try to balance. Okay.
Yeah.
One unit increase in age, okay, to make any impact on the variable with the income already in the model. I need a higher variable. I need a higher coefficient here.
So what you're saying is 1 unit increase of income will not be the same as 1 unit increasing.
Yes, yes.
So so it has to be, for example, 2 units in age, 1 unit in.
Yeah, something like this. Yeah, because you will see in the equations as well later on.
To balance, to make them match.
To balance, okay, because I'm trying to get to y. Okay, and I have ax1 plus bx2. Okay, and this one is in points, and this one is 10 to the power 3. Okay, so if their coefficients are same, okay, and this is changing by thousands. Okay, so if I don't increase a,
it will not be the same way.
Yeah, because for example, this is 0.1. Okay, so this coefficient is 2, and this coefficient is just 2.1. This guy will never have any impact on y. This will always dominate
because of the units.
Because of the unit. Okay, because no matter what I do with this multiplier by 2.1 will do what? Point something something.
Yeah.
Okay, so the overall impact will always be equal to 0 or almost 0. Okay, but if I change something here because of the units, it will have more impact.
And then maybe because of this, you will ignore it while it has.
Because we have this one, if it is not that, it will not affect it much, we will ignore it.
Yeah. Yeah.
So that's why you have to
What
balance.
you're saying, it's not that, like we are increasing the coefficients, so we.
We are not doing it.
No, it will.
The model is doing it.
Yeah.
The model is trying to balance.
But if we ignore it from the start, we will not.
No, now see, the techniques which we have done earlier, okay, they are for categorical variables. So you did not check it yet.
Yeah.
You will not apply, you will not apply t-test to see the effect. The regression is what you will do to see the effect. Okay, and here the criteria for ignoring it will change. It will not be look at the values. Okay, going back to the point was we are trying to understand the relationship between y and x1 and y and x2. Okay, and understanding the relationship means you will look at the sign. Okay, this one is positive, so x2 has a positive effect on y. And this one is also positive, x1 also has a positive effect on y. This up to this, it's no problem. Okay, but the problem comes when you try to interpret these a and b. So if I say, okay, 2.1 is higher than 2, that means x1 has more effect than x2. It's not so simple.
Yeah, it's not true because x1 is.
Could be.
It could
Yeah, could be. We are not always sure. Okay, so that's why we have to sometimes pre-process the data. Okay, and the same thing happens with the AI techniques as well. Okay, so that's why they say you always do the pre-processing and so on for yourselves. Okay. In civil engineering, for example, you are predicting settlement from the load, okay, or you are predicting strength from water cement ratio. So settlement is your output, load is your input. Dependent is settlement, independent is load. In the second case, strength is dependent and water cement ratio is independent. Traffic flow is dependent and time of the day, it will not. It's the wrong. Okay. Okay. Why I'm saying the last one is the wrong example. There's a problem with the independent value. What is that? Time of the day. Okay, it's not a completely continuous variable.
Yeah.
Time of the day has a
hours.
it's the range also. So it's not the ratio. Okay, it's more like an ordinal variable or something like this. It's not completely continuous.
So that we can perform ANOVA on t-tests.
We can do ANOVA, we can do ANOVA, but it will be
So it's
difficult.
continuous depending on category.
Mhm.
The same one, predict a continuous dependent variable from a category.
Yeah, you can treat like this, yes, but you have to like define the categories. Okay, every hour is different category, or maybe every 3 hours, 4 hours, or just the 3 times of the day, night, dusk, or something like this. Okay, we use regression equations in civil engineering all the time. Okay, we don't call them regression because they don't look so simple and cute like this. We see very scary equations with the log in it and exponential in it and cos in it and sine in it. Okay, but by nature they are regression equations. Okay, so when we say the term, when you see the term empirical, if you open any code, steel code, ACL code, empirical formula, right? Empirical means what? What is the meaning of empirical? The word number? No.
It depends on theory.
Depending on theory,
It's equation we.
then you should call it theoretical. Why empirical?
No, because with, there is a to be a number.
There's a real number.
Because it also has weightage.
There are many theoretical
There is
equations which give numbers.
relation between the variables.
Sorry.
There is a relation between the variables and the formula.
Okay. Anything else?
It's similar to this weightage equation.
Similar to this. If you open Stephen Hawking's book, okay, which book?
String theory.
String theory. Okay, what is it? Theory, right? It's a theory, right?
Yeah.
Okay, you will see some equations. You may see some equations which are in numbers, and those are equations.
Yeah.
But we don't call them empirical equations.
Based on experiments.
Yes. Empirical is based on. So this is how the codes are developed.
So not just.
Maybe that's why there is a coefficient.
Yeah.
So for example.
This is how the codes are developed because they yes, this is why we can use it. If somebody, okay, Stephen Hawking comes alive, he is dead, right? He comes alive, he will run away. Okay. Now let's say he comes alive, okay, and he says that I have given this equation in my book. Okay. Next time you are developing a code to make a spaceship, use this equation. Okay. With all due respect to Stephen Hawking and with all due respect to his research, okay, I don't know how he did it, like he was on the chair, but whatever. Okay. We will say no.
Yeah.
Why? Because for the code means something which will apply, something which will standardize. And you cannot do it until you have the proof that this is done. Okay, this is already done. Okay, we did it and we found this result. And now we are almost sure that if you do it, you will get the same result. Only then it is valid for application. Okay, so if somebody comes up with an equation and he has a very good background behind this equation, okay, and what he is saying makes sense and his profile is very high, okay, still, we will not adopt it as a code. The code needs proof. So, and then when you try to go, you will perform some experiments, right? When you will perform the experiments, there is always, they are not performing the experiments blindly. They always have a theory behind it. Okay, so you will do experiments on bamboo fibers and you will do experiment with FRP, you already decided. So you will have a theory before you do start doing the experiment that this is what I'm expecting. And this is why I should have. Okay. That theory may or that logic may still work, but the actual numbers may need some adjustments. Okay. So when somebody will go to adopt it, he has to take it with the adjustments. Okay, you can say, okay, when I increase the percentage of FRP or bamboo fibers, their strength increased. Okay, go ahead. The theory is correct. Oh, I did the experiment. I
At
proved
some
it.
point it will.
Okay, I did the experiment. I proved it. It does increase. What I think is correct, but I still cannot adopt it as a code or as a standard because I don't have the adjustments. So the the equations which are used for design and codes, they are always empirical because they need to be backed up by experiments. And why they look scary? Because they have all the possible factors which can go plus or minus. Okay, so that's why they become so complicated. Okay, the actual reason why they are developed is very simple. Checking the effect of one factor on the other, like what they are saying. Okay, but in the end they become like this, and once you perform the experiments and you collect the data and you drive an equation out of it, and those equations are already in use. Okay, so correlation measures the strength and direction of linear relationship between two continuous variables. Okay, so again, both of them should be continuous. Any of them is categorical, we cannot do that. So yeah, it measures the direction and strength of linear relationship. Okay, sometimes the relationship can be non-linear, and non-linear, can be of different types, such as polynomial. Polynomial, if it is polynomial, a correlation can still give you a good idea. But there are other types of non-linear relationships, as exponential, trigonometric, okay, logarithmic, and so on. So it may not be always the case. Okay, but if it can still work to some extent. Okay, it still work. It is accepted. Okay, so if somebody says, okay, there is a non-linear relationship between these two parameters, but I'm applying the correlation to find out if they are interrelated or not, it's acceptable because we don't have any other means at this level. Okay, so the coefficient ranges from -1 to 1. Okay, so this is the direction, right? Goes minus, that means it is negative, okay, or what we call as inversely proportional, right? Yeah. Inversely proportional, and goes to positive range, it's directly proportional. Okay, so that is about the direction. And then, so 1 is perfect positive linear, -1 is perfect negative linear, and 0 is nothing. Okay, no linear relationship. Okay, and then you look at the value. Okay, anything between them, then you can look at the value to find out the strength of the relationship. Okay. I wrote it right. Sorry.
Need to provide that example.
Civil engineering exams.
Yeah. Okay, so anything you can think about which has a strong positive correlation in the field of civil engineering. Curing and strength. Curing or what is condition? How do you measure curing?
If they cure every day or
Yes, such thing.
until day 30.
We measure the strength of the concrete after this period.
After this.
And compare the strength during
Okay, so strength will have a positive correlation with what?
curing.
Curing time of curing. Okay. A strong negative correlation. Right? What is concrete strength? Concrete strength. Okay. And what
Tension. That's
with what?
as it increases. Or it
Tensile strength increases. So what decreases?
the failure.
It will be like the flexural. Just if we did the flexural test, we will see that it will fail because it has a weak tensile support.
No, but the question is the tensile strength of concrete has a negative correlation with what? Like you said, compressive strength of concrete has a negative correlation with water cement ratio, right? So tensile strength of concrete has a negative correlation with what?
There was something.
No, I know there is something. Obviously, there is something. And it's very easy. Okay, it has nothing to do with concrete mix itself.
The area. cross-
Area, negative,
Steel, number of steel.
negative, or positive. These are positive, right? If we
Yeah.
increase the area, negative,
Yeah.
tensile will increase. If we increase the area of steel, tensile will increase.
Okay.
What will make it decrease? It has nothing to do with the mix of concrete.
What will make the tensile strength decrease?
Decrease.
And
You were very close when you said area.
the workability of the mixture, or if there is any voids or.
The load applied load.
It will make the tensile strength less. No, the load itself is the entire tensile strength.
Consistency of the mix.
Do you know it?
Area,
How do you measure it?
cross sectional area.
Cross sectional area will improve it, right?
If you
Negative. Length,
surface
length.
length,
We're saying area, it's the length.
as length increases, tensile
Tensile.
decreases.
Okay, what doesn't have a correlation? You are absolutely sure that these two things,
They don't.
but they should be in the same, should be part of the same thing. Not like income and strength of concrete. Obviously, they don't have any relationship, yes. But what is in the same
The aggregate,
thing and doesn't have a relationship with each other?
aggregate size with the strength has no.
Really?
It's not super elegant.
I took a class with Professor Mustafa yesterday. He explained everything related to aggregations.
With
And had a, with concrete,
The paste is the one that.
You compare it with the other.
I cannot argue. I cannot argue. He said, you know,
Aggregate weight.
aggregate weight, which weight?
Weight
Like
of
the weight, kilogram or like a unit weight, kilogram per minute?
unit.
Unit weight has. Unit weight has. Unit weight has kilogram,
Maybe the two.
whatever those. It has.
It has.
It has. It's more challenging, right? The last one is more challenging. Okay.
We have to use the same example.
No. Any example.
Example.
Any example. Me saying to my daughter, don't do it, and her actually not doing it. No correlation. He will do it.
Negative correlation.
No, it has no correlation. Sometimes you have to check with her. Are you all right? Like we say, and she doesn't. And you have to check. You all right? Maybe she is sleeping. So she is in her own mind. So no correlation. There is no correlation. Yes. Anything which is in the same experiment or in the same field, but it has no correlation with each other.
It's hard to find no.
Yeah, because everything is like related to each other.
I hate. Just a little, or you're just gonna ignore. If it's near,
Zero,
near
it's not
zero.
completely zero.
Yeah, near zero. Okay, near zero. Did it make your life
I don't
easier?
think, wait a minute. I don't think size of aggregate affect this.
No, it does. It does.
Because it was someone that just
Yeah,
Mostly.
it has the other factors. The whole design is based upon aggregate gradation. Any type of concrete. even the asphalt concrete. It's based upon aggregate gradation, so it has an effect. The aggregates has an effect. I wrote something, but like obviously, like for example, the strength of the concrete and the time when you cast the concrete. No, right? Or the day on which you cast the concrete. No,
Yeah,
the strength of the concrete and
but
Uh,
the day is affected by the temperature at that day.
temperature. The temperature of that day is not part of the day, right? It's not part of the day. I can have a very cold Monday and I can have a very hot one. Okay. And you guys can have a very good Wednesday, Dr. Amuna, a very bad Wednesday. Okay, so no correlation. I cannot say. Okay. So we have this data, right? The beam deflection data. Okay. So this will give you the correlation between the beam load and deflection. Okay, so let us have a look at it. It will draw. No, I don't think so. It may. The correlation can come from the graphics. I don't know whether it will draw or not, but it's a value in the end. So this is the test for correlation basically. This one is a test for correlation, and this is where you put the variables. Okay, so these are the variables, and this is the data file, and you have to change the read command as well. So one thing you can see that they always, when they open the file, we always store the data in one of the variables. So here it is beam data. Okay, so we maybe the other way, but in all the codes you will see that the data from the file is copied to a variable, and then the variable is used.
So it.
Yeah. I'm an expert in reading, right? I'm an expert in the read command. And so many times when you don't. It's 0.99, right? Did the plot as well?
Just
Yeah, plotted as well. Okay. So the correlation is 0.99. Did it give the p value?
1.32 into the power minus two.
I mean, the t is correct, right?
Yeah. It's 95% confidence.
95% confidence interval for the correlation. Did you change it?
Yes,
So it's working in a magazine. Do you change it?
yes,
Do you have the file?
yes.
Where is it?
Page,
No, there's a file.
this page.
What?
You see,
Why is it not showing there? When you set the directory. Go there again.
When you set it, it does not show.
yes, yes. You can change it.
Change this. And okay. Then you are copying the read again. Okay, because it's data. And here it is beam data.
So can I here?
You can either take beam from here or put beam here. This up arrow. You can put beam here and keep this,
Here,
or you can make it beam data. No, it's small. Beam, okay, underscore. Okay, no, it's the same. It's both. Okay. Okay, now you see two things here. One is the correlation coefficient, the other one is the p-value. Okay, for the correlation coefficient, they calculate its t statistic, because correlation is basically taking the difference at each data point, it is taking the difference between the two values. Okay, so for each data point, you can have a correlation value. For each data point, you can have a correlation value. This correlation is called the Pearson correlation. You can have a look for the equation of Pearson correlation and on the internet or in the books. Okay, but correlation coefficient is like the entire data set itself. Okay, so if you have, for example, 10 points for load and deflection, so there are 10 values of correlation. For each point, there's a correlation. Okay, then you see the final correlation, which is 0.9 and something, and you see the 95% confidence interval of correlation is. Okay, so this is showing that there is the entire distribution of correlation. There are many values of correlation. This one is the average, the mean value. Okay, got it? Okay, and then for this data set, they have calculated the t statistic and the p value as well. Okay, and we are following the same rule for the p value, that we have 5% error. Okay, so the p value goes under 5%. Okay, then we will accept the null hypothesis, right? That there is
If it's,
accept the null hypothesis.
if it's less than,
5%,
yes,
5% or less.
yeah,
5% or less. Okay, we'll accept the null hypothesis that there is the null hypothesis is what? The equal to, right? Yeah, what's the equal to here? Basically, what we are saying is if p value is less than 5%, then we say that load has a significant effect on the deflection. Okay, so we are rejecting the null hypothesis. Right? We are rejecting. If p value is less than 5%, there is, we are rejecting the null hypothesis. Okay, well, null hypothesis is always equal, right? Null hypothesis says there is no effect. Okay, So when the p-value is less, we say the load has a significant effect or significant relationship, not the effect, sorry, not the effect.
It's relationship.
A relationship with the deflection. Okay. So another important point here which came up.
Correlation.
Correlation means it's just giving you there is a relationship, but it does not tell you what is affecting what. Get my point? So now you have a strong relation between load and deflection, right? If I put load in the first column, deflection in the second column, or I do the other way around. If I put load in the second column and deflection in the first column, I'll get the same value. Whether I put dependent in the first column or whether I put independent in the first column, I will get the same value. They are not considering the cause. They are saying that yes, there is a relationship, but what affects what? Is load affecting deflection? We know that load is affecting deflection. Okay, but somebody comes from computer science and he says, no. Deflection is affecting load. Using correlation, I cannot say no. Okay, I can punch him, then he will go silent. Okay, but correlation is not an indicator of effect and cause. Correlation is not an indicator of cause and effect. Got it? It's an indicator of relationship. Clear? Okay. Now, if you go in the, so this one gives you the p-value and the p-value is less than 5%. On the basis of that, we are saying it's a strong correlation. Okay. So it is comparing the correlation value with the normal distribution. Okay. And if the correlation value is, compared to a normal distribution has less than 5% probability, we say it is strong. It is significant. We will reject the null hypothesis. Okay. If you look into research papers in which correlation coefficient is used, or in the books, statistics books, you will find a very convenient solution. They don't calculate p-value and p-value. They say if the correlation is more than 0.6, strong. Less than 0.6, not strong. Get the point?
Yes.
Now the problem is, what about 0.599?
Because 0.6 is there.
Huh? But you are very close to 0.6, right? If they say 0.6 can be considered, then what happened to 0.59? Okay, what about 0.61? It's very close, right? So that's why we have this. Okay. Those people who say 0.6, they are putting hard limits on it without considering the distribution of the correlation itself or the distribution of the data itself. Okay. But this method of t-value and p-value, it considers the data as well. Okay. So in some cases it has happened with me that the correlation value is low, the mean value. What you see there, the last one.
Mhm.
The mean value is low, but the p value is also less than 5%. So even the low value is considered significant because it is looking at the entire data set. Got my point? Okay. So okay, then we go to the simple linear regression. What we are doing here, linear means it's linear, right? The equation is linear, but you see here. Okay. Simple is what we use to indicate one value. Okay. So the advanced form of simple will be multiple. Okay. Simple and multiple linear. So we have simple linear, multiple linear. But okay. So here you see the equation y equals to our dependent b naught, beta naught, which is the intercept. Okay. So the absolute minimum for y. If you remove x from the equation, y equals to beta naught. Okay, and we also call it the intercept or anyways. Then we have beta 1, which is the unit change of the effect of unit change of x on y. Okay, and then we have the extraneous variables, which we did not consider in our experiment. Okay, like temperature or whatever. We did not measure them, we did not consider their effect. So then you have the error bill, okay, which should take care of these things. Just at the right time. Okay. So we'll play and come back. Just remind about this. Sure.
بالنسبة للغاية يمكن يكون عمره حوالي 66 من الناس تغيروا يصير مسلمون.
لا ما نبغي.
هو المفروض 55 يقولون إن 55 وايد مبكر.
ما نبغي.
يقولون إنه هو يخليه يعني ما تحصل دراسات من السابقين.
ما تتحصلها 55 يعطوني واحد من 55 تشتغل 5 لا
وايد
60 شنو لها أحوال تحتاج تخيل يعني إيش أحوال تحتاج تشتغل. إيه
وين هو طول الليل وغير ما يقدر يسقط فرصة عن هاي الملكة
شنو
المومنت يعني يجي من الطبع اللي أحسبها أعوض فيها بالعكس ما يطلع لي جواب صح.
شو هي الريجن طلعت ليش؟
ما أعرف إذا من حكي هذا أجرب وأجرب المفروض نحسب المومنتس والرياكشنز زين ونشوف وين اللي هو في الدايجرام ايش الانترفل تقدر زيرو المومنت عشان إن في هاي الانترفل نطلع الإيكويشن. زي وين قطعتين المفروض هني قطعت بين مني يعني 8 و 10.
لا أنتي لازم ما تحددي وين قطعتي.
على حسب شو اسمه
لا على حسب معليش من الدايجرام كنتش ما شفتيه.
زين
هاي عقب عشان تتأكدي.
اوكي
يعني قطعي كنتش ما تدرين الصفر الصفر بتكون عند الإيت.
اي
بس ليش قطعتينا هني؟ فهمتي احنا قاعدين نحاول نطلع وين المكان. إذا قطعت هني خلاص قطعتي في المضاف أصلا.
اي
فالإيكويشن ما بتكون ضابطة. أبي الإيكويشن تشمل المكان اللي فيه صفر قبل مش مقطع.
يعني قصدك اقطع اخذ
سكشن على مسافة ما تدرينها. المسافة اللي انتي قاطعتها هي اسمها اكس.
اوكي وبعدين اخذ المومنت حسب مثلا البداية اللي يقول ام 2 تقول هاي
اي
واللو بس بيكون عندنا رياكشن واحد مثلا او 2.
اي رياكشن واحد الثاني بيكون واحد.
لا يعني مثلا لو قطعتها مني
لا تقول واجد بعد يعني عليها هني. وعلى مسافة اكس.
ولا كانت قبل يعني اقللها
لا
اكبرها مثلا انا وايد قللت الايام
لا تروحي واجد صوبي.
فاذا قطعتها مني واخلي
المسافة unlimited. لا انتي المكان اللي بتقطعيه ما تقطعيه. خلي الهدف كذي عرفتي؟ المكان اللي بقطعه هو اكس. اكس ما ادري
يعني مثلا يعني حددت هني بس لازم بعرف
لا ما
انه
بعدين بتعرفين. اي بتعرفين بعض المسافات يعني انا مثلا اللي سويته
انا عارفه فاهمه الكونسبت لكن بعدين اطلع ايكويشنز بعدين احاول اشوف
الحين انا قطعته على مسافة اكس هني مثلا. اوكي هني بس اكس ادري كم؟ لا ما ادري الاكس كم. اكس يمكن 10 يمكن 12 ما ادري شنو الاكس. فيوم قطعته اعطاني ايكويشن جنرال ايكويشن حق المومنت. هالجنرال ايكويشن بسويها equal to 0 عشان اطلع شنو؟ لان ام سي is equal to 0 اكس اكس بتكون شنو؟ اكس بتطلع لي المسافة من الادج للاكس. هاي الاكس لا الرقم اللي بيطلع بيكون من الادج هني 0 المومنت.
اي
فهمتي؟ فعشان اطلع مثلا المسافة from the start بسوي 12 minus x يطلع لي المسافة from the start كم.
فهمت الحين
عرفتي؟
الحين بسوي
مكاني قطعت ما اعرف كم. اذا عرفت كني الكونسبت في المثل بالضبط. فانت ردي سوي الايكويشن، تقدرين انك بعد تقطعين هني صوب الرولر بس تطلعين بالصاج
تصير اي وايد صغيرة.
لا اذا قطعتين هني كأنك قاعد تقطعين مكان الزيرو
بالضبط.
عرفتي؟
لأن هاي مكان الزيرو
مكان الزيرو مكان زيرو اكس مكان زيرو اكس الرولر بعد زيرو الرولر لا في مومنت
في تحت
هني زيرو
هني زيرو الأند والبي.
الرولر ثاني عشان كذا
أول بكون الساعة وعد
إيه.
بس بواجه
وبعدين اسمي وقارني بتشوفي الناس بالاهتمام
واحد واخذين يعني بطلع الأجوبة كامل ولكم
انا اللي سويتها بس قالت لي دكتورة صح قالت شنو صح لا جاوبت
بس أنا ما أعرف من أي أخذ من أي.
قالت صح هاي السؤال بس المشكلة راح احطه في ايه ماكس حق السؤال الثاني يمشي تحلينه بأي طريقة لا 1 بي
1B هديته أنا هديته
انت عايزة الديتا قلت برجع ليه بس تبين الحلا بأي طريقة
أنا
نيوتن الثانية شكلها نيوتن
وأسهل شيء كأنها أضبط التصميم تستطيع المفروض شوف انت اي شوف احاول اخلص اليومين الاسبوع هذا
بس لا نقول ترى
كيف تتعلم بس يمكن على الأقل يعني إن شاء الله يعني لحد مثلا أو يتأكد إنه موجود من الأول بعد الاستطلاع من تعليم الشيء
Okay. Before we move on, something which I forgot to mention. The correlation which we calculated in the last example with the R, that is called as the Pearson correlation. Okay, there are two types of correlation coefficients. Okay, they have different equations. This one is called Pearson, which is used for relationship between two continuous variables. Okay, the down which we did. Okay, our variables were continuous, right? Load and deflection. And then we have the Spearman correlation coefficient, which is used for categorical and continuous. Okay, so yes, there is a way to calculate the relationship between a continuous and a categorical variable. Okay, using the correlation coefficient, but that one is different. It is called Spearman, and its equation is different and so on. Okay, so it's completely different, but it still has the same range, -1 to 1, and so on. Okay, so when you go into modeling and do these things, you will find sometimes that there is something different which is applying to something which the original one doesn't apply, like this one. Okay, so the original Pearson correlation coefficient does not apply to categorical variables. Okay, so the Spearman applies, but the Spearman has a completely different equation. Okay, but we still call it correlation because it follows the same range and the same rules. Okay, so it is still between -1 and 1. Okay, -1 means this, 1 means this, and so on. Okay, so there's another thing which we call as R square, right? You have heard about R square, right? So R square is normally for regression or equation which has continuous values. We can calculate R square for categorical variable equations as well. Okay, and I mentioned for categorical variables, we have a different type of regression, which is not linear. Okay, we still call it regression. Okay, So there are many terms which we take from one context and apply to other context, although we are doing something completely different. The equation is not same, the working is not same, the variables are not same, but we are still applying it because the final result is almost the same. So in terms of correlation coefficient, the first one gives you -1 to 1 between two continuous variables. The second one gives you same range and the same meaning between a categorical and a continuous one. Got it? Okay. So we are talking about linear regression and simple linear regression. So what was the meaning of simple linear? Simple means what? One value. Okay. One input. One independent variable. Okay. So it's the same. So you can just run it in the same sheet. If you open it, you don't have to load it again because already there. The beam data is already there. So you can see now we are using the same same variable. You can see beam data. Okay. So basically, this is the function Lm, which is supposed to create the linear regression model between load and deflection. And you can see here, it shows deflection depends upon load.
Yeah.
Okay. This is the logic which you are applying. So we are giving what is dependent and what is independent. Okay. So according to our logic, this is what? Independent, dependent. Depends. Okay, and this one is independent. Okay. Somebody switched it, you will still get the same answer. But the logic is wrong. Okay. This is what I explained earlier. Okay. What did you get?
I think this is the deflection.
These are the statistics. This is the model, coefficients. Coefficient is the model.
So
Okay.
this is the
So,
These are results.
sorry,
These are results.
the coefficient is the model results. The results of the model is in the coefficient table. Okay. So what is the first estimate? The intercept is 2. Exactly.
2.1.
So deflection equals
2.189.
2.19.
Yeah.
Then what is the other estimate?
It's the error.
Huh?
Error.
Error?
Standard deviation.
No.
It's T.
Going down.
Oh, down is the root.
0.15.
0.15 plus or minus. Okay, 1/6.
X.
Huh?
Now we multiply this by X.
X. It was load, right?
Yeah.
This is your equation. The other things which you see here are supporting evidence for your equation. Okay.
The T value.
So, sorry.
T value.
So yes, with the coefficient you have the what? The standard error and the p-value and then the p-value. Okay. So the for each coefficient, the null hypothesis is this variable does not have any effect on my dependent variable. This is the null hypothesis. Okay. So when you look at the p-value for the coefficient, if the p-value is less than 5%, that means we will reject the null hypothesis. Okay, and rejection means this variable has a significant effect on the other variable. Got it? Clear? Okay. The standard error. So it's like a standard deviation. Yes, it is like a standard deviation. So this is mean estimate is the mean estimate. mean coefficient. Okay, mean coefficient. Because what happens, I believe it's in the other slides, but I will just tell you the logic. And this is why I asked what we mean by regression. Okay, so when deflection was 2, load was 5. Okay, so if this depends upon this, then I need to multiply something with it to get to 2, right?
Yes, yeah.
Okay, so for example, we multiplied
0.1.
0.5, 0.5,
0.1.
whatever, 0.1, it will give me 2.
But you will add the.
You will add, yes, we'll add this one. Okay, so 0.1, something, that's whatever. Okay, so if I do this, then I will get to 2 when load is 5. Next value, the deflection is 2.5 and the load is, let's say, 5.2. Okay, now I cannot multiply the same thing with this value to get to 2.5. It will not give me 2.5. Okay, so the coefficient is not a constant value. For to match every value of deflection, I should have a new value of coefficient, right? But the model can give me a new value of coefficient. Okay, so the one which you see is the estimate, the mean, the most expected value, the value which gives me most of the answers correct, but it's not the only one. Clear? Okay, so if I have 50 values, then I actually had 50 coefficients. Okay, to match this, to match the variable with the value, I actually had 50 coefficients. So the standard error is like the standard deviation of those coefficients, and the t value is basically mean upon standard error. Okay, and that t value is compared with the standard normal distribution, and you get the p value for that. Okay, and the p value is less than 5%. We say the effect is significant, the coefficient is significant, otherwise not significant. Okay. Now this is simple linear regressions. We have only one variable, so your task is very easy. Either deflection depends upon load or deflection does not depend upon. If the deflection does not depend upon load, your model is done. You don't have anything else, right? Okay, so there is no model there.
That's no.
Yeah, there is no model. Okay, if there are multiple variables, 3-4 variables, we have load, we have water cement ratio, we have temperature, we have reinforcement, and so on and so forth. So you will have multiple coefficients, right? If there are 4 variables, you will have 4 coefficients. Okay. Maybe some of them do not have p-value of less than 5.5, less than 5%. Okay, that means what? The effect is you will accept the null hypothesis. The effect is not significant. Okay, the effect is not significant. Okay, in that case, we have to do the filtering. Okay, now people do 2 types of things in this case. If you have half variables which are having effect and half variables which are not having effect. So I had 4, 3 have an effect, 1 doesn't have an effect. So there are 2 ways to report it. There are 2 ways to report it. One is they keep all of them. They keep the model as it is. And they use the model and these coefficients and the p-values and the t-values to show that this one had an effect and this one didn't have an effect. Okay, so they keep the full model. They keep the full model and they say, okay, and you can see the full model, which one has an effect, which one doesn't have an effect. But they keep the full model in the end. Okay, and the other approach is if this one doesn't have an effect, why is it in a model? Filter it out. Why should I have a model of 4 variables if one of them doesn't have an effect? I'll take this one out. I'll have a simpler model with 3 variables, but both these ways are correct. Okay, acceptable. Okay.
It's depend on what you're dealing with, right?
What? No, not what you are dealing with. Who you are dealing with. Okay, will he be happy with this approach or this approach? Both of them are correct. Okay. So yeah, so the null hypothesis mentioned, yeah, and you see you have what else you have in the model. So you have the residuals means error value. The difference between the actual deflection and the deflection given by the model. The equation. Okay. Yeah. Based on these coefficients, the expected coefficient, the mean coefficients, okay, the mean estimates. So based upon that, the model calculates the deflection and it compares it with the actual deflection, and then you have the residual. The difference is called the residual. And obviously, if you have 50 values, you have 50 residuals, right? 50 actual values and 50 values which are taken from the model. Clear? Okay. Now you understand when I will calculate the value from the model.
So this is the average.
I guess, sorry.
The average of all the errors.
Which one?
The residual standard error. It's the mean error or the average error.
Yeah, sort of.
For all of the 10 or 8.
I believe something else. Residual is the end. The standard
Standard
residual standard is something else.
on 8 degrees of freedom.
Yeah, so I believe it's divided. It's divided. Residual is the difference between the actual and the one which you got from the model. Okay, and standard residual is, I believe, all the residuals, okay, added together, divided by the number of by the degrees of freedom, something like
So
that.
the average of the
Not exactly an average because you do the square root and stuff.
okay.
It's not exactly an average. Like you do the standard deviation.
Okay.
It's more like a standard deviation. Okay, so I was saying that, for example, if I need the actual, I need to calculate the deflection at a particular value of load. Okay, I will take the load from my data, and this one will give me the deflection. So I will have two deflections at the same load. One is this one, the other one is what you already have from the experiment. And then you are comparing between them to get the residual. Okay, understood? Clear? Okay. Now, why do I need the model if I already have the deflection and the load?
You
The
don't
data
have
is more accurate, right?
don't have it for all of them.
We don't have for, okay, so the model is developed for not for these values, for some other test data, right? Okay, the data which is not used in modeling. Okay, just some basic clarifications here. Okay, so what were they looking at? Yeah, multiple R squared, the R squared between the model and the actual values. Okay, and the R squared goes from 0 to 1. R squared goes from 0 to 1. If it is 1, then it means best squared. Yeah, it means something fishy as well. Think. One is
Positive.
and positive. Yeah. Okay, and it works on the values. Works on the values. Okay, what does it mean? What is the impact if it is works on the if it works on the values or it works on the mean? It doesn't matter. Shouldn't matter, but it matters here. In some cases, so you have two things here, which are about the accuracy of the model. One is the R square, the other one is the residual. Residual is the error, the difference. Okay, the difference. And the R square is how the model changes according to the change in the actual value. Okay, the change in model as per the change in the actual value. Okay, so what does it mean? A very true case for Karachi. So you have your high school exam, right? And in Karachi, in Pakistan, the high school exam are at the central level. So make one central exam for all the schools. They do it here as well.
Yeah.
No, yes.
Not for all
In
of
different
them.
communities.
Yeah, but not for all of them. One of them. Same exam.
Yeah.
Same example. Okay. So it happens that somebody like me would not get good marks, let's say. Okay. And my parents are asking me, why didn't you get good marks? Okay. So I tell them that the exam was so tough. Okay. And nobody got good marks. Okay. Nobody got good marks. So then they may say, no, this person got higher than you. Okay. I would say, yeah, he got B. If the exam was not tough, he would have got A. So he was an A student, he got B. I'm a B student, I got a C. Getting my point. So you see that I'm following the trend, but the values are not same. Getting my point. Okay. The exam is tough. So all our grades went down. So the trend is down. Okay. But are the values following the same? No. Okay, he is in his own world with A's and B's, and I'm in my own world with C's and D's. Okay, we didn't have it by the way. Starting over, he got a D and easy. Okay, but it happens. Okay, it happens. So they can be that the values are completely different. So the residual is very high, but the R square can still be close. Okay, R square is more like correlation. We did the correlation between load and deflection, right? Are they the same values, the same type of values? No, the values are different. Okay, the correlation was very close because it was showing that when this value increases, this one also increases. But it doesn't mean they are matching point by point. That if this increases by 1, this also increases by 1. No. Okay, so the residuals tell you about the amount of error. And the R square tells you about the trend, if the model is catching the trend or not. Got it? Okay. So you have people who invest in online trade, right? You guys use that? Want to decide? Yeah.
It's
Boosted inscription. You spend 5 minutes, 500 BD golf, no problem.
If you know.
Ah,
you need
I said 500 BD gone.
Gone.
You don't have to know about it.
Okay. Good.
Gone, yeah,
Gone,
gone.
yeah, that's
to
it.
generate, but money it's a little.
Very good. Okay. There was a comedy play, Urdu, Pakistan. A man came and he said, "Oh, I lost this, I lost this." So whatever he said, the other man said, "You are, you are earning haram." So it's going in haram.
True.
Okay. So what you are saying, right? He said, "My car, you are earning haram, spending haram. My house, or something. My house blasted." He said, "Oh, you are earning haram." So, anyways, the point was, going back to the point, that people who invest in these things, they usually they can see the trend because going up or down is easy, okay, but they cannot catch the values. Okay? So sometimes the trend looks upward, but the values are completely what they are thinking is completely different. Okay, so that's why you have to look at both things, the residual as well as the R square. Now for AI techniques. For AI techniques, R square can be very tricky. Okay, because R square is basically between the model output, okay, and the actual output, and the trend between them, the variance between them. Okay, which works very well when you have an equation like this, on any sort of equation, because the equation goes in a particular trend with the values. Okay, but the AI models don't do that. Okay, they AI models actually are doing real regression. In one value they can go up, the other value they can go down. But there is no trend. They are going up and down just to match the output. The AI tries to match the output. Okay, so it is trying to reduce the residual. Okay, it does not have the criteria of R square. It has nothing to do with R square. Okay, that's why even in the last week lecture, okay, there was a guy who kept on saying, no, you should use shape value to calculate the coefficient. You cannot do that. Okay, the shape value only tells you where the model is going when you take this value out or something. Okay, it does not give you the coefficient. Okay, the coefficient is a fixed value. You understand the concept? Okay, if I take this value out, the model goes up and down, but the whole model goes up and down. Okay, but this value tells me a unit increase in L will do what with D specifically, and whether this unit increase is from 0 to 1 or 100 to 200, it doesn't matter. The effect will be same. I'll have the same 0.16 time effect. Okay, but with the AI techniques, it's not like this. Okay, there are techniques to find out how much is the effect is negative, positive, but it's not the coefficient. Right, Mama?
Yeah.
Okay. So, and with AI technique, R square is usually not a good, or you cannot rely on R square. Okay, that I got a good R square, or my R square is very bad, so throw it out. No. Okay, your model can be still be very good with a very bad R square if it is for AI models. Okay, machine learning model. But equation, obviously, the equation is not fitting. Okay, it's not giving you good R square. You should think about it. Okay, you should not use it. Okay. The regression has 3 assumptions. The regression model has 3 assumptions, and any statistical model has its own assumptions. So before you already discussed assumption for t-test, for ANOVA, correlation. Was there an assumption?
Not causation.
Correlation doesn't have an assumption.
It's negative, positive, or zero.
Okay.
1 between 1.
What was the assumption for the variables?
The variables
Must be the variables must be what?
They must be continuous.
Continuous.
And gets good.
Continuous. Okay. Dependent, independent will show. Okay. So so all statistical procedures have their assumptions. So when you apply it, have a look at it. I have an MSc student who is trying for 3 months to satisfy the assumptions. He already did the difference in June. Okay. But the examiner said you are saying there follows this distribution, where is the proof? Okay. So when obviously when he did that, he didn't, you know. Okay. So but now I'm telling you guys, so if you decide, okay, I'm going to do this model or this type of model, I will do this test or that test, go and have a look at its assumptions. Okay. Then you can see if you are following it or not. And if you are not following it, you can still use the model, you can still use the test, but with some pre-processing. Still possible. Okay. So it's not like, okay, what I will do if I cannot do this. You still have different ways to do it. Okay. So residual, as I mentioned, observed minus predicted. Okay. So there are 3 assumptions. Residuals versus fitted plot should show no pattern. Okay. Regression. This is regression. So the model is going in its own trend, and the actual values are going randomly up and down.
Yeah.
Okay. So sometimes the value is up, sometimes the value is down. Sometimes the error is positive, sometimes the error is negative. If it is always positive,
Not cancel.
it's biased. Okay. If the error is always positive, that means what? Observed is always higher. That means your model is always underestimating. So it's unusable. Okay. That means you are missing something which must be added. Okay. Otherwise, the model is always under predicting. And if the other way around, okay, the error is always negative, that means this is always overestimated. Okay. So there must not be any pattern between the error value and the the plot of the model. Okay, the error should be on both sides, and if possible, in equal amounts. Okay, in some cases, the extreme values are yes, the most extreme values are up, but the rest of the errors are down. Okay, this is also not good. And by the way, this assumption is also true for your AI models as well. Okay. So you cannot say, okay, I'm doing AI model. If all the residuals are positive, no problem. No, it's a problem because it is showing the model is on one side of the graph. It's only basically what it means is. So, for example, if the model is always under predicting, the model is always underestimating. That means the model is only good for lower values. For higher values, not working. Got it? And the other graph. So in that case, maybe there is a factor, some specific factor difference between the lower and the higher values. You may have seen it in concrete design, or I forgot the equation. Okay. There were some equations somewhere, concrete steel somewhere, I don't know, I don't remember, but there were limits. Okay, for example, depth. I remember the depth. Okay, so there were some equations. If the depth is up to 300 millimeters, use this equation or use this.
Or the limit depth and
As the depth and the depth. Okay, so if this happens, that your model is always on one side, maybe you can put a limit and have two models. That may solve the problem because model is always just fitting on these values. So maybe these values have something special. Okay, so just use the model for these values. For this one, we will have another. Right? So, like I said, you always have a now. Okay. The other one is constant variance. Residuals versus credit plot should show a random scatter. Okay, same thing. No funnel shape. So they were saying no pattern. Okay, now they are saying that no funnel shape. And then we have the normality, which is the residuals must be showing. If you only plot the residuals, the error, only plot the error, you should see a random distribution. Sorry, normal distribution plot, which is for the random. Okay, and remember the actual model was this, right? This was the model, right? This is your error. And the error is random. If it is not random, yes. What does it say about your experiment or your data?
We cannot
Not accurate?
We cannot rely on
Does that rely on it? How can I improve it? Normalize how?
more data.
More data? Like more samples? May solve the problem? Yes, it can. But they could be. There is an unknown effect which you are ignoring in your experiments. Okay, so the error is not random anymore. Getting my point?
Yeah.
If the error is because of just experimental conditions,
And you're ignoring.
okay.
You will not get the
Yeah, no, if it is because of a specific factor and I am ignoring it, the error will not be random because it is because of the factor. Okay. But if it is, if I incorporate all the possible factors, which I can, then it should be random. Because then the error is just because of minor differences in mix or minor differences in handling the equipment and handling the sample. Okay, temperature, some small temperature variation, then it's fine. Okay, so this is it. So for that, basically, for all of them, we have different types of plots. Okay, this is the quartile plots, basically. Okay, you see the box plots sort of thing. Okay, so you can see how the data is, how the residuals are distributed. If they are normal, that means each quartile will have almost same number of values. Okay, that is a normal distribution. And these two, you will plot the residual with the fitted line, the model line. Okay, and you will see, did it plot for you? Or maybe you have to just add these at the end. You guys still have the same file, right? But it did plot something or nothing.
Four.
Four plots. Right. So residuals versus fitted. Okay. So this is the first two, the one which you were talking about. Okay. So the first two assumptions can be same from these two. Okay, the fitted line.
Application residuals and recent leverage. This is related to.
This is something else. We did not discuss it. I don't know what it is, but we are talking about these two, the first two. Okay, so if you see the first one, the errors are going up and down, I believe. Right? Okay, and no pattern, basically. No pattern, no particular shape.
Also,
Okay, the funnel shape is like this.
Yeah.
Okay, the one which they mentioned in the second point is like this. When you go forward with the line, the errors start doing like this, or the other way around, funnel in the reverse direction. Okay, but they will be converging on maybe the highest point or the lowest point. So they will start getting closer. Okay, but there is no such thing like this. Okay, and
so it's linear and it's.
the third assumption was should be approximately normal distributed. Yeah, the theoretical quartiles and yeah, so in this case you will see if they are following the line or not. For the second graph, this one,
Yeah.
the QQ plot, you will see if they are going along with the line or not. Like the line and the points are following the same pattern or not. Okay. And you can also see it if the line is straight. If the line is straight, that means it's not following the pattern. Like it's not following the line. So there's no normal distribution here. If the line becomes straight itself, the line is like this, right? That is not following. Okay, so this is normal distribution. If the line was straight, then that would mean that there is no pattern. The normal distribution does not hold. Okay, what are the other two graphs? I don't know. I plotted all the graphs. Okay, now using the model, we can create new data set, like I mentioned earlier. Okay, when we are satisfied with the model, we have looked at the R square, we look at the p-value for the coefficients and so on. Okay, before we do that, just a word of caution, which is for the intercept. And you see there's the intercept, right? Okay, and when you created the model, there's a p-value for the intercept as well, right? Okay, is this p-value significant? Is it showing significant effect? No. How much is the p-value for the intercept? For this 2.1.
It is significant. In this one.
P-value.
P value. It's 1.12 percent to the power -5.
So it's very like it's almost zero, right?
Yeah.
Almost zero. So the null hypothesis is rejected. It has a significant effect. Okay. It is significant. In this case, it is.
Yeah.
But if you have some other data set, you develop the model, and the p-value for the coefficient, so the intercept, is not significant.
So it's more than 0.0.
Yeah. Okay. In that case, I mentioned if it is for a variable, you can keep the variable, or you can remove the variable, right? Okay. In both cases, you are right. But here in this case, the statisticians say do not remove the intercept.
Yeah.
Whether it has significant effect or not significant effect, keep it. Okay, because they say that the other assumptions will also vary. Removing the intercept affects the other assumptions, the normality and other things. Okay, so keeping the intercept, which does not have a significant effect, will not have too much impact on the model because it has insignificant effect. but it will help you to use these assumptions. It will make sure that whatever assumptions you made earlier, they are still valid. Removing it will destroy these assumptions. Got it? Okay. So once you are satisfied with the model, you look at the p-value, you look at the R-square value, you look at the residuals, all assumptions are met, everything is done, good. Now you can use this model for a new data set. Okay, so this code is basically, I believe, generating a new data set. Okay, so you can just run it. Okay, but then it will use a model to predict it. Okay, and the model is saved here, I believe. The model. So this is the model. This is generating the data. Okay, so it will generate like data from between 55 and 85. You can change these values and you can have a look at. You can use different ranges. Yes, something happened. Something happened. Yeah, prediction 1 and 2, right? 1.
Model and yeah. That's
Sorry.
what it's supposed to. So this is the model and this is the new data.
What do you mean?
The prediction. It's the same predict model and new data.
No, predict is a function. Model is what is referring to the equation.
Which is the
Huh?
which is the original.
The original model, this model,
Yeah.
the one which
So
is
this one is depending on the model. This one is on value data.
No. We have two values, 55 and 85. Two values for the two values we gave. Okay, so we give a load 55 and 85.
The lower deflections.
This is deflection at load 55.
Yeah, fit.
And this is deflection at load 85. Yes, fit.
And then here it's lower
Here is the upper and lower limit at the same load.
load. Just
Okay, deflection, upper limit, lower limit of the deflection, upper limit of the deflection when load is 55.
not for it.
So this is the expected value, 10.78 is the expected value of deflection when the load is 55. And then you have the upper and lower as well. Same thing, right?
Yes.
Okay. So you can see the good thing is that you have a range.
Yeah.
Okay, so you can you can predict the most expected value, which is the fit value. And you can also see how much variation could I expect. So this becomes a very good tool for design. Okay, because then in the design you have in your mind how much safety should I take care in. Okay, so it's from, for example, the first one is between what and what, upper and lower is how much?
9.9.
11.5 and fit is 10.
10.
Okay, somebody takes 10 and they design for it. Okay, but we know that it can go, it's reflection, right? It can go as high as 11 point something.
So we take
So we can like give a filter of safety, which can cover this much reflection. Okay, so this is how it can be useful. Okay, so for like we did for ANOVA, this is a sample paragraph for reporting the. Why my voice is like this? That my person, right? See. So you can report the results in this way. Okay. So what was your dependent variable? The deflection. What was the independent variable? The load. Okay. So try to write the results you got from the software in this way. Okay. And if you have any confusion about any value, from where should we take the value, you can let me know. Didn't give the F value as well.
degree of freedom for regression is 8, and for residual is
It's infinity. Okay. I thought it's this
1 is for
regression.
1 is for regression,
Regression.
not for residual.
Residual is 8.
It's
The degree of freedom for regression depends upon how many variables you have in the model,
which is
which is 1. And residual is how many values you have, how many residuals you have. So you have, I believe, 10 values, right?
yeah.
So 10 minus 2, 1 for dependent, 1 for independent. This is how you get the degree of freedom for the residual. So number of values minus total parameters, total number of parameters. Right, 4 parameters, then 10 minus 4.
And we said regression is 1. And here is this
No, this is p value. I feel this one, 188.
is okay. And the paper.
What happened?
Yeah, seems.
Not working out. Done?
Yeah, I think.
Ah, okay. What is R squared?
We take the adjacent, it's the same, isn't
Which one?
it? The R square.
In this case, it will be same, right? Okay, then this one. If the number of variables increase, the adjusted R square and the R square will become different. Or in your case, you have only one variable, right? So adjusted is same as, almost the same as the R square. Okay, so adjustment is number of variables.
And 26.
Again, I'm just giving you the thumb rules and the very brief things about these. Okay, there's a whole theory behind the adjusted R square and R square and P value and F value. We are not going in details. Okay, happy.
Point 1. Okay.
Okay, done. Okay, the F value is called the Fisher value, Fisher statistic. It is very often used with regression models only. Like R square, you will find it with other models. Residual, you will find it in other models. But the Fisher is mainly used for regression and also for ANOVA. We discussed maybe in ANOVA, the Fisher statistic. ANOVA is based on Fisher statistic. Okay, the values, right?
Yeah.
Okay, so Fisher statistic is basically the ratio of variance. Okay, when we are doing ANOVA, we are taking the ratio of the overall variance and the variance within the group. Okay. When we are doing the statistic for regression, we are taking the ratio of variance in the model and variance of the actual. Anyone? Yes. Okay. But you will not find Fisher statistic for all types of models. So we don't use it for AI models. We don't use it for regression of categorical variables. We don't use it there. Okay. The regression is used for F value is used for regression models mainly. Okay. And it is very similar to R square. It is very similar to R square, but obviously R square has a range. But Fisher is just a ratio of the values. Okay. So, but in both cases, it's giving you the same concept, it's giving you the same idea. Okay. Is the model capturing the variance of the actual data or not? If the model is capturing the trend of the actual data or not. Okay. R square and Fisher, both of them are pointing to the same thing. But we use it, okay? Yes, both of them are reported. As I said, there could be some minor differences between them. Okay, I'm not the expert, and this is not the course to go into these minor differences, but you get the point, right? Then we have multiple regression, and you see the equation of multiple regression, and now you can see why we are calling it multiple, because there are multiple. Okay. So one independent, multiple dependent, one dependent, multiple independent variables. Okay, I believe, I could be wrong, but I believe there's only one model which gives you multiple dependent variables, which is this model. One type of model, not regression. Regression only works with one dependent variable. But which type of model can give you multiple dependent variables? Non-linear. Any non-linear model, model of which has a log in it. It will give you multiple outputs. Which model gives multiple outputs? Which type of model? Not multiple values, like multiple outputs. So it gives you a strength as well as something else. Output, like number, not the value. Neural networks. Neural networks. Okay. I believe this is the only. Okay. If there are others, I don't know. Okay, but most of the models have this restriction. They have one dependent and they could be multiple independent. So multiple independent with an equation is called multiple regression, and Y is it's the prediction, and then there could be other, and then you can see an example from concrete. I gave the instruction specifically to AI to give me examples from concrete or civil, and it came up with these examples. Okay, so this can be one example, and this is how you can. This is the syntax in R. Obviously, it will not work because we don't have the data. Okay, but you can see the thing here. So you can upload a data. You can generate your own data, and you can upload it. Okay, so strength is depending upon this plus this plus this. Okay, and it will take the data from here. Not the file name. You have to read the file and store it in data. Okay, so I don't know. Data equals to data. I don't know. It will work on this. May mean it's a command. Anyways, we don't have that data, right?
Yeah, and maybe we need to store the data and
We need to-
before this.
Yes. But I didn't give you this data, right? Concrete strength. We have concrete strength data. We have, right? What are the variables in that? Do we have these variables? Water cement ratio, age, and there were two data sets. One concrete, sorry.
There is strength, no, mixed type, but there is
Concrete strength data. Only
this one,
concrete data.
strength test data.
This one.
No, this one, strength test data.
This is
No, this is different.
It has water center.
This is what I need to. This is like project.
this from
Okay.
lecture.
No, yeah.
There is this one, it has water concentration certificate.
Only, right? It has pass. What is pass? Anyways, it's just a syntax in R. Okay, otherwise there would be a full code there. Full code is not there. That means just okay. So the syntax is very similar to what I've already shown you. Okay, for the simple linear regression, it's the same actually. Okay, did I give you this?
No, so
Let's take, no, we don't.
Sure.